Hello there, math analyzers. Welcome to your Chapter 10, Lesson 6 notes all about sinusoidal modeling. So, what we're going to do in this lesson is we are going to look at some real life applications of our sine and cosine functions that now we understand how to interpret their equations or build an equation based on a scenario we are looking at. So, what are some of the situations that will yield us sinusoidal models, sine and cosine functions, right? Those would be things like, here, let me zoom out so you can see all my beautiful pictures, right? Things like Ferris wheels. Well, we were seeing those back in chapter 9. They actually come in handy again in chapter 10 when we're looking at our sinusoidal functions, right? Tarzan, clearly swinging along his branch there. This is old Nader's golfing. Swinging on a swing is a cosine function, the cyclical back and forth. And of course, Spider Man, when he's swinging over a building, that's a sinusoidal function. Waves and planetary motion. Pretty cool, because all those things, these are all cycles. These are all cyclical motions that can be measured, right? And so, as we're doing any of these cyclical motions and these movements, we can actually measure exactly what's going on and model it in a function equation. So, it's pretty neat. Sine and cosine can help us with a lot. Sound waves, right? Not just tidal waves, but also sound waves, things like that. So, very cool stuff that we're about to look at. So, here is a sinusoidal question about good old Evelyn swinging on a swing, thinking about trig, as one does. And she realized that her height above the ground can be modeled by a periodic function using her height equals 3 cosine pi over 3t plus 5, where t is representing the time in seconds. Okay, so on the graph below, let's actually graph Evelyn's movement. So let's use all these little points here to help us with graphing Evelyn's movement in the swing, if this is the function that she is using, right? So, okay, let's start with the easy stuff, right? The stuff that we learned first. Like the amplitude is 3 and the midline is 5. That's the D value, and it means y equals 5 is her midline, okay? So if we're going 0, 1, 2, 3, 4, 5, 6, 7, 8. So there we go. We go up the side. We do still need to make sure we have a scale. We can see what our X scale is, by the way. It's 30, 30, 60, 90 degrees, 120, 150, 180 degrees, 210, 240, 270 degrees, and then 300, 330, 360 degrees. So instead of our usual radians, there's pi over 2, here's pi, here's 3 pi over 2, and here's 2 pi. Instead of our usual radians, we actually have degrees along our x-axis this time. Something a little different, right? If our midline is right here, y equals 5 for good old Evelyn on her swing, and we know that our amplitude is 3, that means that we are going to be up 3 from this 5, which is, let's see, 5 plus 3 is 8 for our max. And then we are going to be down 3 from our 5 as our midline. So 5 minus 3 is 2 for our minimum. So we know where our max and our min are. Okay. Do we have a phase shift present? Do we have a phase shift present? A phase shift is when we move horizontally, so left and right. And we do not. There's no phase shift present. There's no C term present. But there is a B term. There is a B term, and it's pi over 3, right? So my B term, pi over 3, let's kind of convert that back into degrees. So that's 60 degrees if we're thinking in terms of degrees. Okay. That means our frequency, right, can be considered pi over 3. All right, that's what our frequency can be considered. And that just means that if I'm figuring out, oh, I'm sorry, I didn't put 0 for C when we determined that we did not have a phase shift, right? That would mean that my period is taking 360, 2 pi, and dividing it by pi over 3 and figuring out, okay, where do I get the full curve? Okay, where does the full curve end up? So really, your period, let's see, if it's normally 2 pi over 3, okay, if that's normally what it is, we could actually convert that into degrees, which would be 360 degrees divided by 60 degrees. Well, that's going to be 6, right? That's going to be 6. So let's think about that. If my period is 6, so my period is 6. Oh, gosh. Wouldn't that mean that it's going to take me a little while to get to that? Well, let's look at it. We're going to have a high of 8, a minimum of 2. So a frequency here that gets us to 60 degrees. Gosh, are we going to be every 60 degrees? We're going to have 6 of these? Whoa. Okay, so let's see. If cosine starts high, so she's starting high, and then she's going to end at 60 degrees back high, that means the middle 30 degrees is at our low of 2. And that's going to mean that between those is where you hit our zeros. And this is approximately what we're looking at. And there's going to be 6 of those. Wow. There's going to be 6 of those because we got to get to 360. So now from here to here, and then we're down, and then middle. So another one. Well, that makes sense, right? With a swing. A lot of back and forths. So then here to here. So your middle down here, and middles of those cross the midline, hit the midline. So what a periodic does, keeps going. So here to here, there's your middle. And then in between those are your midlines. There we go. By the way, this would be up off the ground, right? Where we're not touching the ground because we're on a swing. Here to here, your middle, and then the midlines in between those. Look, if you got that, you got the main things you need. And then one more time, here to here, the middle, and midlines of those. Whew. There you go. Wow. So every 60 degrees, we have a full cycle. 6 full cycles between 0 and 360. Whew. There we go. 1, 2, 3, 4, 5, 6. There's Evelyn's function. Pretty neat, huh? Okay, well, here's old Naders' problem. So, I've actually shown him how this is a thing, right? Old Naders out on the golf course working on his swing. And as he was doing that, he decided to just start swinging his club back and forth like a pendulum. He knows the club he's using is 42 inches in length because it's a 3-wood. He told me that. And he knows that he's keeping his club 2 inches from the ground. So he must have measured that with a tee, whatever tee he's using, right? Then he timed that it took 5 seconds for one full swing back and forth. Ugh, 5 seconds? Why couldn't it have been 6, Naders? All right, well, here we go. Let's create a cosine function to model his swing. Are we going to sketch that, or are we just going to create the function? Yeah, we can sketch it. Okay, so let's see. We're going to need an A value, perhaps a C value, perhaps a D value, a midline, and a B value. And how about a period? Okay, so we'll get all those fun things in. And let's do just a nice little graph here. And then we'll do a sketch. So what are we creating? A cosine function. So that gives us an idea as to how we're looking for this, right? So y is going to equal a cosine b times x minus c plus d. And so we'll get all those pieces on the insides here. Now let's think, if he's counting cosine up, so when his swing is back, then we do not have a phase shift again. So that would be a 0 for our phase shift. So he's just counting cosine from up in the back in his back, or his backswing to forward swing to backswing, I guess I should say. Okay, if he's doing his pendulum that way. Now, we know the club length is 42 inches, but we're still off the ground 2 inches. So really, if we're thinking about our max, it's 44, and our min is 2, if you're thinking about that, because you're never hitting the ground. It's never going to be 0 for your height differential, right? So if we're talking about height from Nate's hand, that's essentially what it is, not necessarily the ground, but from his hand. When you're thinking of the height of that club, that's that distance, okay? From his club to the ground. That's your pendulum swing. Okay, so yeah, that makes sense, because 42 inches. So that's his max versus his min. Yeah, we're good. Okay, took me a sec. Timed that we took 5 seconds for a full swing. Now, wait a minute. If we said this, we got to do a quick calculation, right? So 44 minus 2 is 42, which we had already determined, and divide that by 2 to get 21 as our amplitude. So that's what we needed to figure out using that amplitude. It also means that 44 as our max minus 21 for the amplitude gives us 23 for our midline. So y equals 23 is the midline. So if I'm sketching, and here's my 2 inches off the ground, and here's my maximum of 44, my midline right here is your y equals 23. Okay, and then we're 21 above on each side. 21 above, 21 below. So on each side of the midline for that particular thing. Okay, so you've got your amplitude of the 21, and we're still starting at the point we usually start at, which would be the top, right? And then heading down to that 23 midline, and then let's see. So 5 seconds, right? Let's think of 60 seconds, 1 minute. How many times would we have, right? So if you think of the frequency in a minute, 60 divided by 5 would be 12. So your frequency, or your B value, would be 12, which means that your period where one full curve is occurring is that 5 seconds, right? So that 5 seconds is the period where one full swing occurs. And actually, that's exactly what they said right here. For one full swing, that's your period. Okay? And if 60 seconds is the time we're doing this based on, then we're going to have 12 of these occur every 5 seconds. You're going to have a full swing if he's doing his pendulum correct. So that's an awful lot for me to put on here. Let's do this. 1, 2, 3, 4, 5, 6. We'll do the 30 seconds. So we'll just get 6 of them in. Okay. I'll back up here. And then this is actually, hold on, 30 seconds is actually over 1 right there. If we're doing our sketch completely correct, this is 25 would be your last valley, and there would be your last peak. So your peak, and so these are 20, 15, 10. Did I do that correct? Oh, it wouldn't be by 5 there. So that would be 2.5 seconds later. So this is, I'm just confusing you right now. These are not 5-second intervals right here. These are 2.5-second intervals. These would be your 5s. And 1, 2, 3, 4, 5, 6 of them. Okay, so there you are. And your peaks, so here to here, and then to here, and then there we go. There we go. Back up. Back up. That shouldn't be there. Down, up. Perfect. So if I'm sketching, and this is just half of what should be happening. But again, when you've got things moving quick, this is what happens. Yikes. Woo. Woo. Not pretty, but a sketch nonetheless of getting those cosine curves in. Really, all I was supposed to do is create the function to model that. So let's just put that in red so we can really clearly see it. Our A value is 21, and we're using cosine. Our B value is 12, and we do not have a C value, so 12x would be here. And then plus 23, because we're up 23 for our midline, that would be our cosine function to model this behavior. Now, if I did a sine function instead of a cosine function, remember that sine starts at the midline and then goes up. So technically, if I went here, if I came into here, I could create a sine function for this exact same thing, right? And so if these were, this should be 2.5 seconds, and this is the max 5 seconds. So in between those, so halfway in between, because 5 seconds is peak to peak, then half of that, so, oops, how about I use the calculator that's on the screen? 5 minus 2.5 is 2.5, and then divide that by 2. You're looking at 1.25 seconds, so 2.5 plus 1.25 seconds gets me at 3.25 seconds. So that would be my C value if I'm using it that way for seconds. And then that particular equation, if I'm looking at it as a sine function, is mostly the same thing. So 21 would stay the same. Sine would now be here. It would be 12 then times x minus 3.75, because we came in right 3.75, and still plus 23 at the end. So that's your alternate sine function. Okay, because of where we have to start, where we have to come in and start for a phase shift. So we were asked for the cosine function that I boxed in, but if you want the sine function, we have that too. This is pretty neat, right? Because they match. They're only 90 degrees apart from being the same function. So we really can use either sine or cosine to describe these movements. It's awesome. I love this. Okay. Now the Beckett's, some of my BFFs, told them I'd write a question about them, so here it is. They rode a Ferris wheel. Now, mind you, they are not usually adventurous people, but, you know, Elena told Mike, let's ride a Ferris wheel. So they did. Admittedly, Michael was nervous. So Elena decided to help him figure out how long the ride would be. She watched while they were in line and found out that it took 1 minute for a full trip around. She asked the attendant about the height, and he told her the platform was 6 feet off the ground and that the height of the wheel itself was 60 feet, my bad, 60 feet high. So create a sine function modeling the movement of the Ferris wheel and graph it on the axes provided. Cool. Well, if the height of the whole wheel is 60 feet, I'm going to go ahead and assume they meant diameter of the wheel, but it's a Carney. They may not have all the trig background that they should when you're dealing with a wheel on a daily basis, right? So I'm going to go ahead and say that our max here is going to be 66 feet in the air, and that our minimum is the 6 feet off the ground that we are. Okay, so I'm going to go ahead and start that way. That'll be the first thing. After that, let's see. So if I've got 60 between them, right? So let's do 60 divided by 2. That's going to give you my amplitude. That means my amplitude is 30 feet, right? And if let's see, do 30 feet, 66 minus the 30 feet. Oops. 66 minus the 30 feet gets me at 36 feet for my midline, right? So 6 feet plus 30 feet gets me at 36 for my midline. So my D value is 36 feet. So Y equals 36 is the midline. So that's pretty cool. We got that going on. We do not need to have a phase shift here. It says create a sine function for this. It says to create a sine function for this, right? So I know specifically that I'm going to need y equals a sine b times x minus c plus d. And we did already agree that let's not write a phase shift in there because let's start it, right, for our sine function at the midline, right? We'll start it at the midline and go from there. And that one full trip around is 1 minute for one full trip around. Ooh, so this is 1 full minute around, right? So if we're starting at the midline, because that's where sine would start, then go around in 1 minute gets you the full sine curve. So there would be a frequency of 1, which is a B value of 1. Let's plug that stuff in. We get y equals 30 sine x plus 36. Let's get it on there, right? Okay. Let's do a minute down here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So what? 60 divided by, let's just do it a lot easier than that. Let's go by 10. So 10, 20, 30, 40, 50, 60. Let's do that. 10, 20, 30, 40, 50, and 60 seconds. And so this is where we'll end the ride, right? 0 is where we'll start the counting of 1 full rotation. Okay, so now upwise, can I do by 6s? 6, 12, 18, 24, 30. Yeah, that'll work, right? That gets me to my 30-foot thing. And then this is still 6 feet off the ground. And the 36, this next one, is my midline. So I like that. There's my mid. Okay, and then we've got, 42, 48, and then plus 6 more is 54, and then up to 60, and 66 is the max. So that's pretty cool. So we've got plenty of room to get all those on there, right? So our max and our min. So let's say 30 is our halfway point, and that is where we're going to be back down here to 0 because we start at our 0 or midline, and then at 60 seconds, we end at the midline. So halfway between 30 is 15. That's going to be our max. And then halfway between these is 45. That's going to be our min at 6. And then we'll connect. There's the Ferris wheel ride for good old Michael and Elena. It's a circle, so it really doesn't matter where I'm starting it to describe it, right? We're starting this up at the middle of the circle for the Ferris wheel, okay? But that's exactly what happens. That's the circle, and it's spread out over time. That's what sine and cosine do. So, yeah, let's try some of these on your own. Think you got some waves? I think you got another one of these Ferris wheels. You can choose to do a phase shift if that's what you so choose. But choices, right? On where we're talking about those, depending on if you want sine or cosine. And we're done. So I'll see you guys soon. Good luck with your application of real world trig problems. Have fun. Bye, guys.